Good evening and welcome to the third presentation of the five-part webinar series, Troubled Waters. My name is Richard Witham and I'm the chair of the Greater Sudbury Watershed Alliance. Joining me on screen is Terry Louise, the executive director of the Federation of Ontario Cottagers Associations, Bree Edwards from the Ballet Living with Lakes Centre, and Dr. Sapna Sharma, our speaker for this evening. The Greater Sudbury Watershed Alliance recognizes the ancestral land on which we live and work as the traditional territory of the Ojibwe, Odawa, Potawatomi, Algonquin, and Métis peoples. This territory is covered by the treaties of Robertson-Huron, Manitoulin Island, and Treaty 9, with Wikwemikong remaining unceded. We offer our gratitude to the First Nations for their protection of and teachings about our earth and our relations. May we honor these teachings. We're recording all of the webinars, and links to the recordings will be posted on our respective websites. So those of you who are unable to join us this weekend or this evening, and anyone else for that matter, will still be able to view the presentations. The Greater Sudbury Watershed Alliance acts to promote, protect, and advocate for improvements in water quality and healthy watersheds. We have representation from 23 lakes and creek stewardships and 2 First Nations. Although much of our focus is on the protection of the local watersheds, we also respond to municipal and provincial government activities that reduce environmental protection and increase risk to aquatic environments. And I wanted to just take a moment tonight to address some of the issues with respect to Laurentian University. Certainly everyone in Ontario has probably heard about the financial situation at Laurentian University, and all of you, I'm sure, locally have heard that of what's going on in the university, and the fact that they've filed for creditor protection, and the fact that they only had one bank account where they put all the money in. So all of the research funding for students, professors, etc., have been what went into that pot, and so everything's currently frozen. And I don't want to discuss the wisdom of the financial officers at Laurentian, but I do want to suggest how important the Living with Lakes Centre is to the Sudbury area. The fact that they've done an amazing amount of research, which has informed us about issues that are of importance in terms of environmental protection. Much of their research also focused on acid rain and influenced a lot of the responses that took place. And it's really important that we continue to maintain the Living with Lakes Centre. And so I would encourage everyone locally to stay aware of the issues around Laurentian University, and if necessary, we may have to advocate and push for support for that particular organization, because if we lose our funding for a lot of the environmental issues, we're going to be making decisions that won't be based on hard science. So I'd encourage you to stay involved and to be watching that particular issue closely. We're also very grateful to have partnered with the Federation of Ontario Cottagers Associations and Ballet Living with Lakes Centre in the presentation of the Troubled Waters webinar series. All 3 organizations have worked very hard on the development, promotion, and delivery of this event. And we're also indebted to all of the other organizations and individuals who have helped promote this series. We've got people registered locally across Canada, US, and internationally. And so, Michelle, can you bring up the poll? We just want to know where the people who are attending today, where they may be from, if you can just fill that out. And we'll leave it up for another 10 seconds anyway, so that we can get a fairly good representation of the sample.
Yes, we've got about 150 of our over 200 attendees have already responded, so we'll just give it another moment.
Great. So it looks like we've got, well, 50% from the Sudbury area. Another, it looks like 44% in Ontario, and elsewhere in Canada, 4%, 2% from the USA, and 1 individual from an international location. Great. Thanks, Michelle. Oops, that was me. Okay, Terry, over to you.
Thanks, Richard. My name is Terry Reese. As Richard said, I'm with the Federation of Ontario Cottagers, and we're pleased to be co-hosting this series along with the Greater Sudbury Watershed Alliance and the Valley Living Lake Centre, an important source of important research, as Richard has said. FOCA is an Ontario not-for-profit organization. We've got over 500 member associations all over the province. We represent the interests of Ontario's 250,000 waterfront property owners on the issues that matter most to our communities and our families. We compile a great deal of information on these issues and make them available on our website, which is foca.on.ca. We also have a monthly alert, which we send out on topical issues, which you're welcome to sign up to, and you can do that on our front page of our website. For almost 60 years, FOCA's members have identified water quality as the #1 concern and interest. COVID or not, our freshwater systems are facing many challenges and threats. We believe through understanding these complex systems more thoroughly, we can all build an appreciation for their dynamic nature and ultimately build a stewardship ethic so that together we can do our part to keep our lakes great. I'd like to thank in particular the 600 volunteers who participate in the Ontario Lake Partner Program each year. It's a long-standing partnership between FOCA and the Ontario Ministry of the Environment, Conservation and Parks, and it provides valuable data that informs many of the questions and research that you'll be hearing about through these webinars. The Lake Partner Program collects data on phosphorus levels, water clarity, calcium and chloride data, and this chemistry also figures into this chemistry information figures into the important and interrelated issues of climate change, invasive species, and habitat alteration on ecosystems. Many of these issues you may hear from Dr. Sharma and that are of interest to her lab at York University. We're blessed with an abundance of fresh water in Ontario and with a lot of thought leadership, including our world-class speakers that are a part of this series, and they're going to be addressing some of the most important issues facing us in the years ahead. We hope you enjoy this webinar and appreciate the important messages that they have. I've been asked to provide just a couple of logistics about Zoom. I'm sure many of you have become accustomed to, but you'll be muted, all of you as participants throughout the presentation so that we can have uninterrupted enjoyment of the presenters. If you do experience technical difficulties, if you're having problems with your sound, for instance, you can just log out and log back in. If you have difficulty getting back in, this is also being streamed to the YouTube FOCA YouTube station. What else? If you at any point you can pose questions to the speaker using the Q&A button. You can find the Q&A by either mousing over your screen or tapping it if you're on an iDevice. And we would encourage you to enter your questions at any time, and we'll address them at the end and try to get to as many as possible. Tonight we're going to allow you to upvote or like the questions that you see. So if you see one you like and you think you'd like to hear the answer to, then please you can indicate that through the Q&A function. Thank you for attending tonight. We hope you enjoy the presentation. Stay safe and be well. So over to Bree Edwards.
Awesome, thanks Terry. Good evening everybody. I'm Bree. I'm a research scientist with the Ministry of the Environment, Conservation and Parks, and I'm lucky to be stationed at the Valley Living with Lakes Centre in Sudbury. The Living with Lakes Centre is a state-of-the-art research facility that's on Laurentian campus and on the shores of Ramsay Lake, right in the heart of Sudbury. And it's an amazing institute because it's home to the Cooperative Freshwater Ecology Unit. And this is a long-standing and really unique partnership that brings together ministry and other government folks like myself with academics from Laurentian and other institutions, as well as industry partners and other stakeholders. And so today, it is our great pleasure, and I'm thrilled to be introducing my friend and total rock star aquatic scientist, Dr. Sapna Sharma. In an academic context, Sapna is my older sibling. She was a little bit ahead of me in the Don Jackson lab at U of T, and she taught me how to navigate a ton of stuff when I was first starting out. I'll always be grateful for that. Fast forward just a couple of years, and Sapna is now an associate professor at York University. She has a very diverse research portfolio in all things limnology, community ecology, quantitative methods, and applied issues, such as climate change and species invasion, just to name a few. She's got a special knack for generating and mining big, large data sets that span massive spatial and temporal scales to help us understand and make predictions about the ecological implications of environmental change. Sapna is also passionate about removing barriers around citizen engagement with science and math, and she leads an outreach initiative that creates educational opportunities for refugee children who have just arrived in Canada. Today, Sapna will be speaking with us about the multitude of ways lakes are feeling the heat of climate change impacts and what that might mean for the future. Without further ado, please welcome Sapna.
Thanks so much, Bree, and I'm excited to be here and to talk to you about something that I think about a lot. So I'm just gonna share my screen, get everything set up. Find my mouse. My mouse has disappeared. Are you guys seeing the?
We see the PowerPoint, Sapna. You just need to start it.
Okay, so there we go. I lost, perfect.
Yeah, it's good now.
Okay, great. So thanks so much for having me here and for spending your Thursday evening listening to a talk about climate change and lake ice. So before I begin, I just wanted to acknowledge the many collaborators, students, postdocs, and community scientists who are an integral part of all of this research. A lot of when you're working at global scales and working with large data sets, it's a big team effort. And I'd like to take this opportunity to thank all of the different scientists involved in this research. So as Bree mentioned, I study the effects of climate change, invasive species, habitat alteration on lakes through water quality, water temperatures, ice dynamics, fish populations, and communities. But one of my absolute favorite topics that I research is lake ice. And there's several great things about studying lake ice. And one of them is that people have used ice for centuries. And it's been an integral part of winter culture, winter economies, winter communities in northern countries for many years. So in the bottom left here is a photo of ice being extracted from lakes and rivers for refrigeration before the proliferation of refrigerators. Here's a photo of an ice festival at Lake Louise, and millions of people attend pre-COVID attended ice festivals every winter in around the world. And this really was a great place to build community, be exposed to winter culture, as well as bring in a lot of economic growth to the local communities hosting these winter festivals. As most of you have probably participated in winter recreation activities, hockey, skating, ice fishing, those are all part of our winter tradition and our culture in these northern countries. And up in the top left panel, we've got winter transportation, which are integral to connect remote communities to have access to resources, but also social networks and communities during the winter. And so with that, with the fact that people have used lake ice for centuries, comes data, which is great for somebody who studies the effects of climate change on lakes. And some of our earliest records actually come from religious sites. I'm going to talk a little bit more about this is Lake Suwa, and Shinto priests in Japan have been regularly collecting ice formation dates since 1443. Here we have the bust of John the Evangelist being carried. And this Lake Constance ice record actually starts in 875 AD. And there was a church in Germany that would carry the bust of Evangelist across frozen Lake Constance to a church in Switzerland as a sign of friendship between the two countries. Here we have a little more locally ice record in Lake Simcoe in Barrie that goes back to the 1850s. And part of this ice record involved the local men's club driving a pickup truck with a clock inside the truck. And when the truck sank through the ice was the date of ice breakup. And finally, some of our best, most amazing records actually come from gambling pools. And that's because you have hundreds or thousands of people observing the ice thaw event. And so we can get information to the hour and definitely day with quite a high degree of accuracy because of these gambling pools. And so because of this, and because of all these diverse records and people interested in lake ice, we're able to collect data on climate long before the advent of meteorological stations. And so we can get an understanding of climate from direct human observations even before the start of the Industrial Revolution, which is quite powerful in understanding how climate is changing. And another great thing about working with lake ice is it's a very sensitive indicator of climate. As you all know, fresh water needs temperatures below 0 degrees Celsius to freeze. And so having dates of when the lake freezes in the fall, like early winter, and thaws in the spring gives us an idea of what climate conditions were like in late fall, winter, and early spring. And so it ends up being this fantastic indicator of climate that, as I mentioned in the last slide, exists long before weather stations existed. And so I'm going to walk you through one of the longest lake ice records, and I think one of my favorite lakes to study. And this is Lake Suwa in Japan. And the ice record began in 1443 by a generation of Shinto priests. And it has been followed, this tradition has followed to 15 generations of the same family of Shinto priests. And the reason that they collected this information, this lake ice formation data, was because their local tradition, this religious tradition, is dependent upon ice formation in Suwa. And so the story is that there was a god and goddess that lived together on the shores of Lake Suwa. And sometimes what happens when people live together for too long, they got into a disagreement. And so the goddess moved out and she built herself a shrine on the other side of the lake. And every year, the god would cross the frozen lake with his dragon to seek forgiveness and make amends with his wife. And the priests, the Suwa priests, were really interested in this ridge that forms on the lake. And I spoke with many Japanese linguists and historians to get at what is causing this sinusoidal shape. There was some conversation about whether it's the dragon's tail that's creating this ridge, or is it the god's footsteps? And after a lot of translations and study of the old Japanese text, it was determined that these are the god's footsteps. And so every winter, when the Amawatari forms, this is the ice ridge, the priest holds a purification ceremony and then gathers important leaders from the community to celebrate this event, to record this event. And it was also used as to foretell and predict the harvest, the rice harvest. So seeing the Amawatari was a good omen to the local community for a good, bountiful harvest. So you can see here in the left is a photo from many decades ago to more recently, where you have the same family of Shinto priests recording and celebrating this important event. And so from there, my collaborator from John Magnuson from the University of Wisconsin-Madison went to SUA, went to speak with the local priest, as well as a limnologist. And what they did was they translated the records from rice paper into Excel sheets, into Excel spreadsheets that any scientist can then use, and we can use it to understand many different facets of climate. And I'm going to illustrate a few ways in how we do it. And so, if we look at something as simple as, does a lake freeze or not? That's what we're doing in a particular year in this graph. And so here we've got our time series from 1443 to 2020. The priest just sent us the latest data, and the lake did freeze this year. And on the y-axis, we've got years with no ice. And so what you can see in these tiny bars is that in the first 250 years of the time series, Lake Sua did not freeze 3 times. Let's fast forward to the next 250 years of the data set. And what you can see is that between the 1950 to 1999 period, Lake Sua did not freeze 10 out of the 50 years. So it wasn't freezing 1 out of every 5 years. Since 1990, the lake is actually only freezing twice in every decade. And so here what I've done is incorporated observations from 2000 to 2020, as well as our forecasts. We recently forecasted under climate change scenarios in which years will Lake Sua freeze. And we found that from 2000 to 2050, the lake is expected to be ice-free 39 out of the 50 years. And it's not expected to freeze again after 2040. And so here we have this long tradition, this long religious tradition rooted in community, and it's currently at the brink of loss, and we're expecting it to be lost in the next coming decades. Unfortunately, Lake Sua is not the only lake experiencing ice-free events. And so what we've been interested in knowing are, why are these lakes experiencing these ice-free events? And we're documenting that more lakes in recent decades are experiencing this intermittent, what we term intermittent ice cover. So an ice-free winter. And the strongest relationship, the strongest predictor of whether a lake will freeze or not in a particular year is winter air temperatures. So on the x-axis here, I've got winter air temperatures. And on the y-axis, we've got the percentage of ice-free lakes in a set of lakes that we studied. And what you can see is as we approach that 0 degrees Celsius mark, that lakes are less likely to freeze. Simply going back, it's the other great thing about working with lake ice is it just makes sense. If temperatures are below 0 degrees Celsius, the water is not going to freeze. Or above 0 degrees Celsius, the water is not going to freeze. And if we look at, so here what we did, we looked at 520 lakes around the Northern Hemisphere that have data extending decades to centuries. And we looked at which lakes are vulnerable to this intermittent ice cover. And so in pink, we have identified intermittent ice covered lakes. And in blue are the lakes that continue to freeze every winter. And what we found was the lakes that are more likely to experience ice-free events are found in warmer regions and at lower altitudes. Interestingly, lake depth plays an important role as well. So the lakes that are predicted to experience intermittent ice cover are also those that are larger and deeper. And that is because it takes larger lakes a longer time to cool in the fall. And they also need much colder temperatures to freeze. So in our recent study published last month, we identified that, a small lake could have winter air temperatures around, just below -1 degree Celsius to experience an ice-free year. Whereas a larger lake, they need winter air temperatures below -5 degrees Celsius to freeze. And so this is relating to the fact that these larger, deeper lakes are sensitive to ice-free years. The other thing that affects these large, deep lakes is wind. And so when you have the initial skim of ice at the beginning of winter, if you have a strong wind event, that will contribute to breaking up that ice and perhaps relating to an ice-free winter. The New York Times helped develop this. We worked with a graphic artist at the New York Times, and they helped us summarize our results in a pretty map. And basically what we have here in orange are lakes that no longer reliably freeze every winter. And in gray, lakes that continue to freeze. So Lake Sua, as I mentioned, was one lake that's experiencing intermittent ice cover in recent decades. And when we examined 1.3 million lakes around the world, what we found was that actually there are 15,000 lakes that are in a similar situation, where they used to freeze every winter and in the last few decades are experiencing ice-free years. And what you can see is that they're in more southern regions, also along the coast. And what you can't tell from this map is that they're also the deeper lakes that are sensitive. And so what happens under climate change scenarios? And so what this animation is doing is going through different climate change scenarios that the IPCC has called out as relevant. And so if we have 2 degrees Celsius warming, it's sort of our best case scenario at this point, we're expecting about 45 to 50,000 lakes that may experience intermittent ice cover. If we go towards 4.5 degrees Celsius, which is a warming predicted with no climate change mitigation, you can see that that number increases to thousands of lakes, eventually up to 215,000 lakes that may no longer freeze each winter. Let's take this situation to the most extreme. So recently we wondered, well, how many of these lakes that are currently intermittently ice covered going to permanently lose ice? And what we have plotted here is the decade during which that lake is predicted to have a final freeze event. And what you can see under moderate greenhouse gas emission scenarios, that we have 429 lakes that are predicted to be permanently ice-free within this century. Again, southern lakes, coastal lakes, as well as the large deep lakes. And in regions that are, experiencing right now at that cusp, that threshold of losing frozen winters And so these are the lakes in, deep lakes in Switzerland and Germany that are, moving towards winters on average that are becoming too warm for lakes to freeze. On the other hand, without any climate mitigation, in this RCP 8.5 scenario, we predicted almost 5,700 lakes that may experience permanent ice loss. This is devastating ecologically. I'm going to go into some of the examples later on, but just as a primer, lake ice sort of acts as a lid on a lake. It acts as a reset button. And in years where you don't have lake ice, we see higher evaporation rates. We see warmer water temperatures into the summer, and also increased phytoplankton growth, increased prevalence of algal blooms, some of which may be toxic. So lake ice cover really is necessary to promote water quantity, to keep our freshwater quantity available, and to all of these communities that rely on it, as well as healthy water quality. And as I mentioned, deep lakes in southern and coastal regions are the ones most sensitive to losing ice cover permanently in the near future. So Lake Constance, which I introduced to you in Germany at the beginning of the talk, there is no climate change scenario where we could predict that this lake would ever freeze again. This is true for 179 other deep lakes in Germany and Switzerland that are expected to permanently lose ice cover this decade. A lake closer to home that you're probably all familiar with, Lake Superior, as well as Lake Michigan. We've been recording using ice records going back to the 1850s for bays in Lake Superior and Lake Michigan. And under high greenhouse gas emission scenarios, we're predicting the permanent loss of ice from both of those lakes in the 2060s. And under moderate greenhouse gas emission scenarios, which is our, what we're hoping for at this point, in the 2080s. And as you can imagine, millions of people rely on Lake Superior and Lake Michigan for their fresh water. And that could have, quite devastating consequences for this huge ecosystem. What about lakes that still freeze? So there are approximately 50 million lakes that freeze every winter. And even those lakes are experiencing warming. And so what we've plotted here are 24 of some of the time series that we have going back to the 1850s. And we've got ice on dates and ice off dates. And what we've found is that lakes are freezing later, about 11 days per century later, breaking up earlier in the spring, about 7 days per century. And what we're documenting for tens of lakes across the Northern Hemisphere is on average 2.5 weeks less winter and ice cover per century. And the last time this was done for lakes around the Northern Hemisphere was in 2000, led by John Magnuson, and his data went to 1995, and that's about here. What you can see and what we've quantified is even faster rates of ice loss since that last big synthesis that was done. And so we're quantifying that ice is being lost at about rates 6 times faster in the past 25 years than they have been in any of the 25-year period going back to the 1850s. And that's an alarmingly fast rate of ice loss. For the future, we're expecting this trend to continue. So, for example, lakes around Sudbury, in Muskoka are still expected to freeze going to the end of the century. But the rates, the days of ice duration are expected to be about 20 to 30 days shorter, which has some ecological and socioeconomic implications. So why? Why is ice melting earlier and freezing later? Well, we've looked at many different time series. We've looked at many of the drivers, and the number one explanatory driver of this pattern is climate change. Increases in air temperature are corresponding to later ice formation and earlier ice thaw. And this may explain in science terms like 60 to 70% of the variation, because ice is really dependent on having air temperatures below 0 degrees Celsius and for an extended period of time. There's other factors, local factors like precipitation, snow cover, wind events that also contribute to these changing ice states. And finally, large-scale climate drivers play a role as well. So things like El Nino Southern Oscillation, the North Atlantic Oscillation, solar sunspots. Because we have such long time series, we can evaluate their contributions. And they do play an important role, but not nearly as, not even close in importance to changing air temperatures. And so what are the implications of losing the lake ice cover? So there are ecological implications and cultural and public health implications that I'm going to go through just a little bit today. So ecologically, this is actually, it's a pretty fun time to be somebody who studies winter biology and winter limnology, because we know that winters are changing rapidly. And what does this mean for the world around us? And for limnologists, what does this mean for life underwater? And it's a pretty exciting time where people are, scientists around the world are really trying to grapple at these questions. I'm going to talk about a few examples. The first is water temperatures. And so this was a fantastic collaboration that I co-led with that involved 80 scientists from around the world. And we've actually included, we were able to, the data from Sudbury, the Sudbury Lakes was included, data from Muskoka was also included as part of this collaboration, which was fantastic to understand how Ontario fits with the rest of the world. And what we did was we talked to lots of people and brought together scientists, and in yellow are what we call in situ data. So data where people have gone to the lake, put in a temperature probe, measured the temperature of the lake for the last 25 years. What you can see is they're quite limited geographically to parts of North America, Europe, close to where universities are. And what we were missing was most regions of the world. And so this is where we teamed up with NASA to get satellite data from them, where they could measure water temperatures from space for the same time period. And they were limited to, monitoring really large lakes. And so between the two of us, between these two groups, we were able to have measurements for over 350 lakes. And going back 25 years, we had small lakes, we had large lakes, and we could cover large areas of the world. And because we were looking at so many of the largest lakes, the lakes that we chose actually represent over 50% of the world's freshwater supply. The other thing I wanted to just briefly mention is that this data is available, as is all of the ice data. I do spend a lot of time making data available open access for everyone to use, so that we can really, as a community, as a scientific community, really promote and our understanding of how lakes work and not be limited by having access to data. And so all of this data is available, as well as the lake ice, if you ever want to see it. And what did we learn? Well, we learned several important things. So first, we found that 90% of lakes are warming, and they're warming at a rate of about 0.34 degrees Celsius per decade, which is a bit faster than the rate of air temperatures warming, and much faster than ocean temperatures. The lakes that had the fastest warming rates, twice as fast as a global average, were the ice-covered lakes. And the idea is, and there's still, some scientific discussion around this, but these ice-covered lakes are now experiencing earlier ice breakup, and that's contributing to a longer open water period of warming. And we talk about earlier stratification. That's the water turning into layers, but also just this open water season, and the longer duration of this open water season is contributing to faster warming rates. Going back to Lake Superior, in our study of all of these hundreds of lakes, Lake Superior was the second fastest warming lake in the world. And, and this comes back to this earlier ice breakup period. We also found that 10% of the lakes were cooling. And I find this pretty interesting because they were cooling for similar reasons. So lakes in Florida and lakes in the Alps in Europe were cooling for similar reasons. They had land use changes that contributed to decreasing the water clarity, and that contributed to lower rates of water temperature changes. There's also lakes in the Arctic in North America, as well as the Tibetan Plateau, that were cooling. And they were cooling because the glaciers are melting around them and inputting cold water into those lakes. And so, even though the majority of lakes were warming at fast rates, this analysis really helped us to uncover why and how these different patterns emerged in lakes globally. And here, it was a complicated analysis, but what I want you to look at is just the color of the circles. And the color of the circles represent the similarity in water temperature trends, but also similar characteristics in climate and also lake characteristics. And what you see is that, lakes next to each other, and even in here, we have underneath these points, there's a lot of different colors in Ontario. Lakes next to each other may not always behave the same way, but they may behave similarly to other places around the world. And that's, I think, the power of looking at, at global data, because it really puts your lake or your region in perspective of what other regions are experiencing as well. And so we identified why are lakes warming faster in the past 25 years. So climate change was the predominant driver. As air temperatures increase, water temperatures increase. And we also uncovered a phenomena of solar brightening and dimming, where the Clean Air Act in North America and the Northern Hemisphere in the last 25 years is really corresponding to a brighter, what we call solar brightening, and increased solar radiation inputs because of less particulate matter. Whereas the Southern Hemisphere at the moment is experiencing dimmer conditions because of more industrialization in Asia that's contributing more particulate matter. We recently also published a review looking at how climate change is affecting lakes globally. And we've talked about here lake summer water temperatures. We've talked about evaporation rates. So when you have when you're experiencing no ice, you're experiencing, or also less ice, you may experience higher evaporation rates. And there are lakes around the world having decreased water levels. And John Small in a couple of weeks may introduce you to some lakes in the Arctic, small ponds that have completely disappeared because of high evaporation rates. We have changing mixing regimes that, all of these physical changes in the water correspond to changes for the biology and ecology of the lake. We've seen studies talking about increased algal blooms, some of which may be toxic because of increased warmer water temperatures. And that can have a huge impact on life in the water, but also for people. When you think about Lake Erie in Toledo, Ohio, experiencing that toxic algal bloom at the intake pipe, affecting hundreds of thousands of people and their accessibility to clean water. We have changes to fish habitat. And, I've done lots of work looking at thermal habitat of fishes and the spread of smallmouth bass invasive fishes through Ontario and around the world because of warmer conditions. And before I wrap up, I just want to talk a little bit about what this might mean culturally and also for public health. So in our study where we quantified intermittent ice cover, there's a postdoc on the project, Kevin Blograve, who's here today, and what he managed to do, which was pretty amazing, was quantify the number of people who use or who have access to a lake within a driving distance, within 1 hour driving distance. And what we wondered was how many people are going to be affected by this lack of ice cover. And so even with a 1 degree Celsius increase in air temperatures, we found, because it's in the southern parts, 100 million people could not, easily drive to a frozen lake. 2 degrees Celsius, we saw 200 million people that may be impacted and have less access to this frozen lake. So what are people using lakes for? And being a scientist and being part of this amazing global network called GLEON, the Global Lake Ecology Observatory Network, we put together a team to get some data on how people use lakes and are they being impacted, these uses being impacted by changing winter temperatures and warmer winters. And so the first example here are from skating races in Lake Mälaren in Sweden. So this race actually originated in the 1600s, 16 or 17th century in the Netherlands. And it's, has kept moving further north as winter ice has become less reliable. You may have seen photos from the Netherlands and all the people out skating this year, sort of to bring a blast from the past. But what we looked at here was the skating race in Lake Mälaren in Sweden. And typically you can, do a race across the lake. That's what the typical race is. In some years, they have to have a shorter loop. And in other years, they'd had to cancel either because they weren't sure if the ice was going to be safe enough and they didn't want to lose too much money, or because it just, the ice just wasn't reliably formed. And if we relate this to winter air temperatures, what you see is in warmer winters, you have either canceled races or these shorter loops that had to take place. Ice fishing. So ice fishing in Minnesota is a huge, huge cultural and socioeconomic activity. One of these ice fishing tournaments may bring in $800,000 US per weekend. So it's quite important to these small communities. Here, what we have again is winter air temperatures and percent canceled tournaments. And what you see is that in warmer winters, we have more cancellations of tournaments. What about ice roads? So this is an ice road in James Bay in Canada. And here the freezing degree days is it's a bit backwards. So 900 means it's very cold. So over here we have colder days, here we have warmer winters. And what we've documented is 3-week delay in the winter ice road opening in the last 2 decades because of warmer winters. And this has drastic consequences for remote communities that rely on these winter ice roads to get access to food, to supplies, and to social communities. And finally, we also were interested in answering the question, are more people falling through the ice? And because of warmer winters, we know from our work over 150 to 650 years that winters are warmer. Is this translating to impacts on human mortality? And so what we did was we put together data from 10 countries and talked to coroner's offices, talked to police stations, went to police stations, went to life-saving societies, and we're able to get some of these amazing time series of winter drownings. And we documented over 400 fatalities in the past 10 to 20 years. And a bit surprising to us, we found an extremely strong relationship with winter air temperatures. And what we found was that as air temperatures, so here we've got winter air temperatures on the x-axis and the number of winter drownings per capita. Generally, as winter air temperatures approach 0 Celsius, we saw higher rates of drowning. And once air temperatures exceeded 0 Celsius, those regions didn't tend to have that many fatalities. Interestingly, Germany is, it's a cold winter in Europe, and Germany's lakes are actually frozen this year, and there have been already lots of documentation of drownings and falling through ice. Italy, so I'm going to talk a little bit about some exceptions. Italy was an exception, northern Italy, and even though air temperatures, these lakes, some of these lakes were freezing in the north and in the mountains, there were very few drownings. And it turns out, you can't go out on the ice until the police say it's safe to do so. Snowmobiling and ice fishing are prohibited. And so they were staying quite safe. The other exception was the territories in Canada, the north. And even though it's cold, they experienced the highest number of drownings per capita of any region that we studied. And it turns out it's related to Indigenous communities that really rely on ice for winter travel, also for subsistence, such as fishing and hunting. And there have been other studies that have documented increased search and rescue events and also increased fatalities, unfortunately. So we were curious to know more about this. Like, when is it the riskiest to be out on the ice? Well, we found the time of ice breakup is by far the riskiest time. And I've already shown you that ice breakup dates are earlier in the spring. And so, you can't, you can no longer go out at the same time as you did in the past, because on average, climate has warmed. The other risky time was at the beginning of winter. And so these two time periods are changing the most. They also are when the ice is less thick, it has decreased structural integrity, and that can all contribute to increased drowning events. This is probably the saddest graph that has ever come out of any of my research, where we looked at who was drowning. And so we divided it into 3 categories: when there's no vehicles, when you're on a light vehicle like a snowmobile, or a heavy vehicle like trucks. And we found that kids under 9 are at most risk of drowning when playing on the ice. You know, being in Ontario, and regardless of where you might be, you've probably heard of news stories this winter of kids, you know, playing out on the ice and falling through and tragically losing their life. The other category are the snowmobilers. It was particularly the ages of 20 to 24, engaging in high risk activity, probably at times under the influence of alcohol, and falling through the ice. So it's quite important that we engage in conversations in our households, in our communities, about ice safety, particularly with young people, because of their high risk to drowning. And so, but I'm going to end in a good news, some positive news. What we found throughout our work is when we forecast ice cover under climate change scenarios, mitigating greenhouse gases preserves lake ice cover. So if we did nothing, if we continue emitting greenhouse gases at current rates, we're expecting 65 to 193,000 lakes that could become intermittent ice cover. If we reduce or cut our emissions by 2050, we're seeing half the number, 41,000 to 90,000 lakes. And under a best case scenario, we're seeing 26,000 to 48,000, another half of lakes. The situation becomes even more apparent for permanent ice loss. You know, with no greenhouse gas mitigation, we could see 5,700 lakes losing ice cover permanently. As we've talked about, that has implications for freshwater quality and quantity. And even curtailing our emissions in the coming decades reduces our permanent ice loss to 429 lakes. And that, you know, gives me some optimism for the future, and some hope that we could really work towards preserving our freshwater ecosystems. So I'm going to end there, and thanks again to the collaborators, and I'll take any questions. Should I stop sharing my slides, Michelle or Bree?
Yep.
Oh, that's great. And we'll invite Bree to join us now, and we'll start to do some Q&A.
I think I need my video feed to be enabled on your end, Michelle.
All right, let's try that.
There we go. Thank you.
Excellent, no problem.
Awesome. Oh, what a fabulous talk. Thanks so much, Sapna. And this new thumbs up option is definitely helping me sort through the questions, and some themes and levels of interest are coming up. So that's awesome. You can still keep adding questions, and we'll get to as many themes and topics as we can. Right at the top of the list, super interesting, given all the data you've been able to collect, we're wondering if traditional ecological knowledge or observations of First Nations in Ontario or elsewhere have been integrated into any of your data collection.
So it's pretty interesting because I haven't integrated myself, connected with traditional knowledge, but it's integrated within our data. which is pretty nice. So the northern, for example, with the drowning study in the north, it's traditional knowledge has been talking about the earlier ice breakup, shorter ice duration, thinner ice, weaker ice, and commenting on search and rescue events and fatalities. The same is true for the winter ice roads. So that data was conducted in keeping in mind of traditional indigenous communities who rely on these winter ice roads, who documented similar findings that as we did. So it's nice that we have this comparator that that can really support both traditional knowledge and data-driven knowledge that I'm doing.
Awesome. Okay, so another top question is about other characteristics of the water that might relate to whether lakes freeze. And people are really interested in salinity. Of course, you know, that's a hot topic for lots of reasons, but is salinization of inland lakes leading to them being more or less freezable?
Actually, no, not these lakes. So we did a simulation to see how much salt you would need to add to make a difference on whether the lake froze or not, and it was in the order of millions of tons into a lake. So at the scale we're operating, we can't find an impact of salinization. But it's a good question. Yeah,
that's good news. There's some interest in understanding the relationship you mentioned between a lower ice clarity and this tendency towards cooling, or a difference in trends of warming or cooling when you have this co-occurrence of less clarity. Can you elaborate on that a bit?
Yeah, so that's related to water clarity in the summer, not the ice in particular here. And basically, when the lake is murkier, darker, you have less solar radiation inputs being able to reach the water's surface and warm up the lake, because it's a simple way to put it. We also found that there's relationships with trees, and so they might be blocking out some of that solar radiation reaching the lake surface, contributing to its warming. So that's those are sort of, it's really related to the solar radiation inputs that are declining because of reduced water clarity.
Okay. You already touched on the idea that larger, deeper lakes are more prone to the impacts of climate. Is there a difference between lakes that stratify or become layered and lakes that don't, in terms of their risk of losing ice cover down the line?
That is a good question. So we
smart people in the audience here.
There are smart people in the audience. It's a pretty good question, because that's something that we're thinking about at the moment. So, I've been using data collected directly by people to this point for the most part. And so we don't have an idea of stratification or mixing regimes. So we're not able, we've always wanted to even put it into our water temperature models. But there's a scientist that I'm collaborating with at the European Space Agency, Istin Wolway, and he's been using satellite records to look at water temperature changes and also mixing regimes and stratification and water quality at the end. And so what we are doing now is we've teamed up, and we're actually answering those questions at the moment. So I don't know the answer right now, but hopefully in the next year or two, we'll sort of uncover how things change by mixing regime and mixing type, and not just looking at something as simpler to measure and to get information on as depth.
Awesome. A future Troubled Waters Forum topic.
Yeah.
Okay, now there's a lot of interest in the idea that the loss of lake ice can impact water quality. And I imagine there are multiple angles on this, but can you elaborate a little bit on some of the drinking water and other qualities of water impacts?
Yeah. So, so as I mentioned at the beginning, this is a big topic of research in the scientific community right now. So it's still a work in progress. And what we've come up with are some hypotheses about how things may work, but this is, something that we're going to keep exploring. So the idea is that when lake ice thaws earlier in the spring, what we have are, so we have earlier open water season. What we're documenting is earlier stratification. Stratification sets up earlier. Stratification is also quite strong earlier. And we're also noticing this longer open water season. So if we connect ice to water temperatures, we can see this pretty nice relationship that, spring water temperatures will be warmer when ice melts earlier, and possibly summer. We're trying to connect it to water quality through ice. I ran some analysis a couple months ago for lakes globally. The connection with ice is not quite there, but it's through the connection of warmer water temperatures. So what we've been finding and what others have been finding is that with water temperatures, we have the higher likelihood of phytoplankton growth. There's this term, blooms like it hot. And you have the higher likelihood of algal blooms, and that's really dependent on water temperature. So the summer water temperatures. And what other people have noticed is that these algal blooms can go pretty late into the fall. So in Ontario, they're documenting algal blooms into September, late September, because of associated with these warmer water temperatures, and that affects our water quality. So increased algal blooms has different effects ecologically. Once there's competition, the algae start dying, it decreases oxygen levels in the lake, which affects fish communities, it affects macroinvertebrates, so that can lead to fish kills. But it affects our ability to go to the beaches and use the water recreationally. But if these toxic algal blooms form, like for example, Toledo, Ohio, it formed at the point of the intake water pipe, then that affects our drinking, directly affects our drinking water supply. And so it's sort of like, it's like a domino effect. You start with less winter, earlier ice off, and it just kind of dominoes through the year.
For sure. All right. Folks are also interested in understanding what other biological impacts there are of changing ice dynamics. So,
yeah, that's a great question. So that's something so this background that I have behind me is from Montana, and that was the last conference I went to in person. And it was the American Geophysical Union Chapman meeting on winter limnology. And basically we had a group of scientists who are interested in what do warmer winters mean for everything in the lake or outside the lake. So biologically, it seems as if, it's not only the changing, lack of ice that might affect nutrients, it might affect fish populations. It's also the changing ice quality. And what that means is that because we're experiencing like more extreme events, like we might get rain in the winter on ice, that changes the ice quality. And that changes or you might have a lot of snow or you might have a little snow, but snowpack also affects the amount of light that penetrates into the water column. And so that affects life underwater. And we've done one synthesis for lakes around the world. It was one of the first in a long time where we looked at phytoplankton growth and primary production under ice and in the summer. And we found that actually under ice, there's a lot going on. There's a lot of chlorophyll, there's a lot of growth, much more than we thought there would be. Not as much as summer, but still quite a lot. And that, these communities are thriving underneath the water. So it's not quite clear yet, but something that we're studying and many people are studying is how does ice clarity and the amount of light that gets through affect life underwater. There's also, things that live on ice, like in Lake Baikal, there's one of the only freshwater seals, and it's super cute, and it lives in like the pups grow in these winter ice caves. And so having ice and, thick ice is super important for this freshwater seal to raise its pups. So it's not only for, underwater organisms, but also some terrestrial ones as well.
I can't believe I didn't know about the freshwater seal. I'm gonna have to look it up.
Yeah.
Amazing. Okay, so one of the questions that's been lingering is about, we know there's a relationship with climate change, but what about with the Industrial Revolution? Is it all connected, or are there any unique signals of industry or changes in other ways that people interact with the world that are impacting ice?
Yeah, so that's a great question. And we actually studied this. So we had two records going back before the Industrial Revolution. So we had ice formation dates on Lake Sua going back to 1443. And then we also had a river in Scandinavia, the Torn River, that had data going back to 1693. And actually the Torn River data was amazing because they've been able to document each year all the conditions, where they were standing, what was going on. And so what we documented, so for Lake Sua, for example, there was a period of deforestation around the lake. And that began in about the 1810s. And we could see that effect on our lake ice dates. They also, at one point became more of a resort town. And that could be observed in our lake ice as well. And so what we found was that, for Sua, those drivers are important. They changed the ice formation dates, but climate change was overriding the other land use changes. However, in other places, there's different stories. So in Toronto, the Toronto Harbor in Lake Ontario, that record goes back to the 1800s as well. But that lake has not frozen. Toronto Harbor has not frozen for decades. And that is directly linked to urbanization and the fast growth of the city. And so, urbanization for the Toronto Harbor far outweighs the climate change impacts. In the Angara River in Russia, that river has data going back to the 1600s as well. But in 1954, it stopped freezing. And it was because a thermal power plant was put onto that river. And so the thermal effluent going into the river from that power plant, doesn't allow for ice to form on that river again. So it depends. And that's why having data from lots of different places and lakes in different situations, whether they be urban, whether they be remote, really helps sort of our overall understanding of how climate change affects these lake ice processes.
Okay, there's a few more questions sort of about the climate change versus.
Okay, great.
So a little bit back to clarity, but specifically browning or brownification. Is brownification having an interactive effect with climate? Is it more or less influential than climate change? What's the interaction, or what's the story between those two? And I mean, folks are mostly interested in Ontario, but of course, you know about all over, so.
Yeah, so that would have been a good question for Norm.
Yeah,
Last
probably
week.
listening right now.
Yeah, so there's singing. I'm not gonna say if Norm's here. I think he should answer that question. We haven't looked at brownification and how it affects lake ice. We have looked at, in our water quality work, looked at how there is widespread brownification. And so I don't want to comment on the direct climate change impacts, because that's not something I've looked at in the data.
Okay. So then the other one is about different types of changes that we're experiencing. So you've obviously shown that overall air temperature and changes in air temperature are highly influential. But what about, and you kind of touched on it, like increased variability in weather events or extreme events, or sort of more just other spin-off things that are happening alongside climate change?
Yeah, so exactly. So extreme events are we've been working on that over the last couple of years, like everybody. And we've been focusing on the ice in different ways. So ice-free years. And that is an extreme event for a lake that freezes every year. And what we found since about the late 90s, we're seeing more lakes experiencing these extreme ice-free years that didn't historically in the past. And so that's one type of extreme event. We're analyzing some extremely late ice formation dates and extremely early ice breakup as well over the past 100+ years. And we're seeing since 1995, over 60 or 70% of our lakes are experiencing like some of the latest ice formation dates and some of the earliest ice breakup dates. Right now, I'm working on the State of the Climate report for lake ice for 2020, and what I had some data from Finland, and these lakes in Finland typically freeze in mid-November, early December. Last year, they were freezing at the end of January or even mid-February. And so, we are seeing more of these extreme events. And when we've looked at them, it really seems to be driven by these extremely warm winter air temperatures. I think you might also be getting at some of these large-scale climate oscillations, possibly. So, working with ice data, we can actually quantify the role of the solar sunspots, El Nino, North Atlantic oscillation. And I didn't show the analysis. It's, I think, one of the things that I find the coolest, but it's pretty complicated statistically. And what we found is that, so using the SUA data and the Torn River data, we found that before the Industrial Revolution, these large-scale climate oscillations were acting at multi-decadal scales. So we'd see the ENSO cycle, the El Nino cycle, was acting at a time period of like 50 to 70 years. The North Atlantic oscillation was also at, multi-decadal. After the Industrial Revolution, and even within really the 20th century, an El Nino cycle is now 2 to 8 years and 2 to 7 years. And NAO, the North Atlantic oscillation, we find, at the 7-year cycle, 15-year cycle instead of these 50-year decadal periods. And then we're also finding that some of these oscillations get stuck in its positive phase. And so that's also adding on to the effect that would be expected by climate change alone. So if you have a strong El Nino year happening every 2 to 6 or 7 years, that's gonna, take you to that next level. And that's what we found, that it takes us to the next level of warming to get to even faster warming rates. And the same is true for the North Atlantic oscillation. So they're all interacting and they're all playing a role to contribute to acceleration, actually, of warming in the last few decades.
Okay, that's a really good segue to the next question that still has some high thumbs up. So if you look at, like, say, the Northern Hemisphere, the predictions for warming are greatest at higher latitudes. But a lot of, I think, what you showed for the risk of lake ice loss is sort of more in the lower portion of North America. So there's a difference between warming rates and the risk of warming rates and the risk of ice loss itself. So I guess, do you have any other elaborations or comments about just sort of predictions across different latitudinal gradients?
Yeah, so that's a very important and a good question. And I'll try to answer it in 2 ways. So it's true, northern latitudes are the lakes that are experiencing the fastest rates of warming. And, the study that I showed today could relate to water temperatures. So we found that lakes at these northern latitudes that are ice covered are warming twice as fast as the global average. And you've contrasted that with the ice studies where we're showing these are still northern latitudes, but they're southern for ice. And I think that's the differentiation that, at this southern border, 50 years ago, those lakes may have frozen every year, but they're crossing this tipping point to becoming in an area where winter air temperatures are no longer below 0. And so it's ice loss is happening at the south, from the south north. And being in Canada and being where we are, we're not expecting to cross over to winters. Our winters are warming, they're warming at fast rates, but they're not going to tip over to having winter air temperatures above 0 degrees Celsius anytime soon. And so I think that's a difference, where that's why the lakes still freeze, but our lakes are also warming faster, and we're seeing more algal blooms because of these warmer conditions.
Perfect. Okay, I think we're going to take 2 more questions. They're very different. One, just because you talked a little bit about evaporation and a little bit about water levels, but you didn't really have a chance to go into it. There's obviously a lot of interest in particular in the Great Lakes water level fluctuations that we've seen. Is that related to warming and climate?
Yeah, so it is related to climate change. So water levels in the Great Lakes is a tricky situation because you have a bunch of drivers acting at the same time. If you look at the last 30 years, you would have seen 30 to 50 years, you would have seen like consistently declining water levels. But more recently, climate change in this region is manifesting in more storm events and higher frequency of precipitation and storm events. And so we're expecting warmer and wetter conditions, and we're experiencing warmer and wetter conditions. So to that end, we have higher water levels because of increased storms, more extreme storms, related to increased precipitation events. But in the same token, losing ice increases evaporation rates. And so that's, I guess, the million-dollar question, like, how are those 2 processes going to counteract one another? And at which point will we see this higher evaporation rate taking over? So in global synthesis, there isn't a clear pattern. We can't say that all lakes are experiencing lower water levels or higher water levels. There's a lot of variation because of also the effects of precipitation.
Okay, that's great. Very, very well answered. And so I think we'll do our last question, and I'm going to broaden it a little bit, but even our most optimistic scenarios are predicting, warming and changes in ice predictability and all those sorts of things. So at some point we have to start with some amount of acceptance and then think about how we should adapt or how we could mitigate some of these impacts. So do you have any personal thoughts about, either from the human use perspective or ecologically, what we should be turning our eyes towards in terms of those types of topics?
Yeah. So I think the drowning study really conveys how important adaptation is required, because our human behaviors have not adapted to these changing winters, and knowledge transmission about changing winters hasn't reached everybody in their everyday decision making, and that can have fatal consequences. And so it really speaks to me the importance of adaptation to warming winters in different ways, and being aware that winters are changing. We're experiencing, winter whiplash, these extreme winters. There's a term called winter weirding. It's just winters are weird. And we're experiencing like super cold events and then also really warm events within the same winter. And that unpredictability requires us to adapt our actions now, especially for us in Ontario, where we do have this strong connection with winter activities, winter recreation. Winter culture is ingrained in our everyday activities. And so I think some adaptation at an individual level is required even before we mitigate greenhouse gas emissions to continue to enjoy winter in a safe way.
There we go. I think that's a great spot to end it. So I'll turn it back over to Richard to close us off. Thanks, Sapna.
Great, thanks, Bree.
So this brings us to the end of our session tonight. I want to thank again all of the people who contribute to the webinar and the audience for their questions. Those working behind the scenes, from FOCA, Terry Rees, and in particular, Michelle Levin, who manages the Zoom webinar system in the background, keeps everything running smoothly. Bree Edwards from Ballet Living with Lake Center for an excellent job on the questions, and our speaker for this evening, Dr. Sapna Sharma. It was disturbing to learn how much global warming will decrease ice cover and change aquatic environments, but it was also encouraging that the greenhouse gas reduction can have such a dramatic influence on reducing this trend. So it was great that you were able to include that information as well. When you leave the webinar, you'll be linked to a survey. We welcome any feedback you can provide about this presentation. And next week at this time, Dr. Andrea Kirkwood will present on, thanks, Michelle, on using the community science co-production model to inform lake management. Thank you very much again for attending tonight. Please follow all the COVID-19 regulations in your area, and good evening.
Thanks, bye.
Bye.